Hi, kids. All right, so you should have already done a little bit with this. So imagine we have a cube. Each side of the cube is d, so it's d by d by d. There is one single molecule. Why we only talk about one molecule? Just to make it simple to start. This molecule is moving in the x direction, and it bounces off the side, and it comes back, okay? And it's moving at a certain speed. So, well, if this molecule moves there and back, the distance it will have traveled is 2d. And because this molecule is moving at a constant speed, because we're going to assume it's an ideal gas, which means it's going to have an elastic collision, which means the energy is conserved when it hits, that if something's moving at a constant speed, we can use the equation v equals d over t. But because it's moving 2d, we're going to say 2d over t. So that t would be the time that it takes to go there and back. And then if I solve for time y, because we're going to need it later, you would get this, 2d over my horizontal velocity. Okay? Now, this molecule, when it hits the side, is going to have a collision. Anytime there's a collision, you should be thinking about momentum. The equation for momentum is P equals mv. Momentum equals mass times velocity. There's going to be a change in momentum. And we said that this is positive mv, this is going to be negative mv. So if you go final minus initial, the change in mv would be 2mvx, if we're talking about mvx, because this is really the x direction. Okay? Well, if you hopefully remember from your previous physics class, that change in momentum is impulse, and impulse is force times time. So I get that, and then time, I can take this and plug that in there, and so you end up with force times 2d over vx equals 2mvx. That's an x. You'll notice the 2's go away, and if I do a little more crazy algebra, I end up with f times d equals mvx squared. Now remember, the whole goal of this was to relate pressure and kinetic energy. So let's see if we can get pressure and kinetic energy. So first of all, you'll notice it looks like I almost have kinetic energy here. But remember, this was a molecule that's only moving in the x direction. Is there something special about the x direction? The answer is no. So it could just as easily be moving in the x and the y direction. So if it was moving in the x and the y direction, if this is vx and this is vy, well, its speed would be v. So you would end up with v squared equals vx squared plus vy squared. But remember, the y velocity and the x direction there's no reason that one should be different than the other if we're talking about an average. So really, our average speed would really be equal to, if it was just moving the x and y direction, it would really be equal to 2vx squared. Okay, assuming, again, on the average, this and this are going to be the same. But it's not just going to be moving in 2D, it's going to be moving in 3D. So really, I should have v squared vx squared plus vy squared plus vz squared. And then again, if we're talking about on the average, they all should be the same, so I'm going to end up with that. And then, if we do a little bit of crazy algebra here, you would end up with vx squared equals 1/3 of the average squared. Okay? All right. So this is going to be like in general, because there's no reason to believe that, it's just going to be moving the x direction. Well, if I want to talk about pressure, so these molecules, when they're hitting the sides, are going to exert a pressure on, the side of this. Well, let's go back. So remember this. We're going to come back to it in just a minute. And let's talk about pressure. So pressure is force divided by area. Well, if you look, I have force here, so let's solve for force. Force equals pressure times area. Well, what is the area of one side of this cube? It's going to be force equals pressure times d squared. Well, if I take this and I plug it in for my F right there, I get pressure times d squared times d equals mvx squared. And then in general, because I want to do this in general, I'm going to take this, plug it into Vx, and look, here I have d squared times d. Oh, that's d cubed. What is that? Oh, that's the volume. So I get pressure times volume equals 1/3 mv average squared. Okay? So all I did is I just plugged some stuff in. Now, okay, again, my goal is, how is pressure related to kinetic energy? So you see, hey, I got pressure here. Okay? This side almost looks like kinetic energy. But remember, our formula for kinetic energy is 1/2 mv squared. So I need to do some stuff to get rid of, I need to get rid of that 1/3. So to get rid of 1/3, what do? I multiply this whole thing by 3. But I need a 1/2 there. So what do I do to get a 1/2? I multiply by the whole thing by 1/2. And when I do that, I end up with 3/2 PV equals 1/2 mv average squared, which is, hey, look, there's kinetic energy. So I end up with 3/2 PV equals the average kinetic energy squared. So here's really what this is saying. Really what this is saying is that the pressure of this whole thing is going to be related to, not kinetic energy squared, what am I doing? Just kinetic energy, okay, is going to be related to the kinetic energy, the average kinetic energy of all those molecules, okay? Well, how do I find pressure? Pressure is, well, really P times V, remember, P times V is either this, or P times V is this, okay? This if I'm talking about the number of molecules, this if I'm talking about moles. Just so I match the equation that's on the equation sheet, I'm going to use this one. You'll notice it would work if I use the other one too, but I'm going to take this and plug it in times P times V. So I get 3/2 NKT equals average kinetic energy. Now, this would really be the average kinetic energy of all the molecules, okay? Well, most of the time what we're going to do is we're going to call this our stored energy in the gas. So this gas has energy if there's more than one molecule in it. This gas has energy. Why does this gas have stored energy? Because the molecules are moving, okay, which is this. So our stored energy for the gas, stored energy for the gas, is going to be equal to 3/2 times the number of molecules times the constant times the temperature in Kelvin. Okay? Now, again, if you would rather, this is like, this equation is not quite on the equation sheet, and I'll show you why in just a minute, but if you'd rather say 3/2 nRT, that's fine too. Okay? But it's written in the equation sheet more like this. Now, if we're talking about one single molecule like we were up here, what is my N? Oh yeah, my N is 1, and this equation is on your equation sheet. The average kinetic energy for one single molecule is going to be 3/2 kT, where you have to remember that is measured in Kelvin. Okay? Because why? Because this is 1.38 and then times 10 to the, let me look at my constant sheet, minus 23rd, I think. Yep, minus 23rd, and it's joules per Kelvin. It's right there. Okay. So there's your equation, and here's what this is saying, and here's why it's super powerful, is that, hey, look, here's what this is saying. Average kinetic energy depends on temperature. Okay? So the average kinetic energy of a single molecule moving around, okay, depends on just the temperature. It doesn't depend on anything else. Okay? And in fact, if you have two gases, if I have oxygen, if I have nitrogen, if I have whatever, water molecules, that if they are at the same temperature, the average kinetic energy for all of the different molecules is going to be the same. All right. Bye, kids.